Today, we actually get to begin our study of calculus. So the first thing that you're going to be doing is comparing everything that you've learned up to this point. Algebra, geometry, algebra 2, pre-calculus, all of those courses together, they're now considered pre-calculus because they're everything before you began studying calculus. So you're going to be able to describe to me what is the difference between what you learned before and what we're learning now. In addition, you're going to need to understand this word limit that we are going to be talking about a lot. So that's something that you want to make sure is in your notebook and that you can define that word. And then you want to know how that they're used. We're going to be talking about two specific problems, the tangent line problem and the area problem. These two problems are the initial discussions that occur when we're learning the two major concepts that we're going to learn in calculus this year. And then we want to know how do these problems relate to the basic idea of what calculus is. So what is calculus anyway? Everything that we've learned up to this point is static. We've learned basic, tiny little formulas that help us get to an answer that were asked in a book. But life isn't in a book. Life is constantly changing. It's constantly having something happen and alterations that are occurring in the phenomena that we experience in daily life. So that's what calculus is all about. It helps us deal with the math that's in our lives. And as we study these things that are happening over time, that's when we're using calculus. So if I were to tell you I'm going to take a trip from Imperial to San Diego, and I tell you, well, I'm going to drive 75 miles per hour, am I really telling you the truth? Because can I really drive a constant 75 miles per hour as I go across the mountain? Even if I put on my cruise control, as I start to go up the mountain, the engine will drag a little bit, and what will the car have to do in order to maintain that speed? Or if a semi pulls out in front of me, I can't just let the cruise control keep running the car. I have to take action so that I don't run into the back of him. Or as I go over a hill and I've taken the cruise control off, if I look at my speedometer, isn't it possible that I could be going quite a bit faster than 75 miles per hour? So now, instead of just simply telling you this is how fast I'm going, now we can ask more detailed questions and study things that are happening across my trip as I travel. As we look at these things, we're looking at a bigger life problem. And very often, life problems are hard to solve all at once. And so calculus gives us that tool so that we can break it apart into smaller problems, get the answers to the smaller problems, and then put those small answers together, and now we have that big answer that we were looking for. And when we do this, our answers are more accurate. So everything that we've learned in math up to this point, our pre-calculus skills, are now going to travel through the limit process. And as we push through the limit process, that's what leads us to calculus. So as we do that, there's three specific things that we're going to need to know a lot about. The first one is secant lines. You first learned these in geometry. It was when we took a chord and it hit two sides of the circle. Well, now we're going to have curves. And so anytime you have a line that hits your graph more than once, then we consider that a secant line. A tangent line. This is that line that skims right past the graph and intersects it only in one point. The limit process. Finding a limit. I want you to look across the room wherever you are right now and look at the wall that you see right in front of you. I want you to picture yourself walking half the distance to that wall, and then again half the distance from where you're now standing to that wall. If you continued this process and only walked half the distance to the wall, would you ever really reach the wall? That's the idea of a limit. Now we know that, with our physical limitations, you would actually cram your face into the wall and probably have a sore nose. But what we're looking at is mathematically, if we were able to measure that mathematically, we would never ever reach the wall. So that's the idea of a limit. We're looking at a boundary or a value that our function is reaching. And there are times when our function may actually touch it or skim right past it, but that's the idea of the limit. Now I want to talk about the tangent line problem. So let's talk about what we have on our graph at the moment. So we're starting with a graph of f of x, and I have my first x value right here, and right up above it I have an f of x. It's considered my y value. And then I go a distance away. And we're going to call that change delta x, the change in my value of x. Now let's talk numerically for a minute. You can see that I'm at about 1.5. So if I go 2.5 units, x plus my change in x, 2.5 units, I land right at 4. Okay, but let's say I don't know what these measures are. So I call them in variable form, my change in x, delta x. So this point here, instead of x plus 2.5, which would have been 4, I now am looking at it in variable form, x plus delta x. So therefore, this y value is my f of x plus delta x. Whatever value that new x2 would have had, then I would plug that in there and find that y. Okay, so what I'm really after in the tangent line problem is I'm looking at this point right here. And I want to know what's its slope. What's the change? What's happening in this graph at this moment? And so I started off by drawing my first secant. Well, you can notice that my secant is a negative slope, but it's really far away from my original point. And so I'm not really getting a lot of information from that. So I'm going to draw a new value. I'm going to make my delta x smaller. So now my delta x, my x's are moving towards my original value of x. Okay, so I've made my delta x smaller, and I have a new value of delta x, and I'm going to draw a new secant line. Now I could find this slope, but then again I'm asking myself, is that really an estimate of what's happening right here? So I pick another point. I'm starting to make delta x become really, really small. And I say, what if I draw a line between those points? I'm still dealing with secants because my points are separate and I'm hitting the graph in 2 points. But what if I got so close that delta x was like 0? Then I would be hitting the graph in only 1 point, and I could actually estimate what was happening to the slope of my graph, even though it's a curve and not a straight line. I could use the tangent line to estimate the slope right at that point. And that's the whole idea of the secant line problem. Okay, so now I want you to use tangent lines to analyze what's occurring in a graph over time. So we're going to say that this graph describes me driving down the street, and at this point, right where time is 0, my position is 1, I look way down the street and I see the signal light ahead turn green. And so what's the natural occurrence that we would do? We would step on the gas. And so right here, where time is 0 and I see that green light, I floor it because I want to hit that green light. And so as I'm getting closer, there's cars in my way. And I still have my foot on the gas, but I'm taking the pressure off just a little bit. Look at what's happening to the slope. Very steep. When I first saw that green light, I was racing. I wanted to get to that green light. But right here, then I've kind of lifted my foot off the accelerator. It's still on it, but I'm easing up the pressure because I don't want to run into anybody. And now as I'm approaching the light, I'm watching it turn yellow. So as I get here, look at how much slower I'm going. I'm still moving forward. I'm still accelerating, but not as fast as I was at the very beginning. Now, right here at the top, I've just lifted my foot off the gas, and I'm going to apply the brake in just half a split second. So I lift my foot from the gas, I'm watching that turn yellow, and I'm like, oh man, I've got to slow down. And so now I'm pressing on the brake, and so now you can see my speed is decreasing. And it's decreasing some, but not as much as it is going to be right down here, where the light actually turns red and I have to slam on the brake to make sure that I stop at the light. So over time, you can see I increase my speed Still increasing my speed, but it's getting not quite as fast of an acceleration. And then up here, I lifted my foot off the gas, put it on the brake, and started braking the car. And you can see even in the braking that the slope changes as time goes by. In this graph, we're looking at the representation of the fraction of a city's population infected by a flu virus. We have it plotted as a function of time in weeks. I want you to look at the graph and tell me, first, is the flu spreading more rapidly at t equals 1, 2, or 3? And then look at the latter half of the graph and tell me, is the flu spreading more rapidly at t equals 4, 5, or 6? And explain your answers. Okay, for this problem, I don't want you putting the answers in the Google Doc form. I just want this one on paper. I'm trying to get you guys to do the calculations ahead of time to save us time in class as we go over this example. So we're going to be exploring the slope of the secant line passing through 1.1. So 1.1, no matter what other points you're using, this will always be one of the endpoints. We want to find what is the slope approaching as we come from the left of 1.1 and then as we come from the right of 1.1. So you need to put all of these values into your function f of x equals x squared and find your y values first. And then using the points, with 1.1 being always one of the points that you use, find your slopes along the entire table. And we'll discuss it tomorrow in class. Now we're going to discuss the second of the two important concepts that we learn in AP Calculus. So we're going to talk about area under a curve. Notice we don't have formulas that give us areas under curves. We know circles, we know rectangles, we know trapezoids, we know triangles, and those types of shapes, but we don't have anything for a changing curve. So we have to use what we know and adapt it to something that we don't know. So in this case, you can see that we're drawing rectangles using the height of our function, our f of x, and then having a width. So let's just use some numeric examples. If I'm looking at this graph and I say, okay, we're going from this point right here to this point right here, and we're going to say that's 1 unit. Well, if I can fit 4 equal rectangles inside, then each of these are 1/4 unit long. So the width of my rectangle is 1/4. I already have one side. Now I just need to find the height of the rectangle and multiply them to get the area, and then add up all of the little rectangle areas. So then I would look and I'd say, well, what x value is this? And I would determine, oh, that's 1/4 because 0 is right here. So, and it's the same width as all my rectangles. So this, although it's saying f of x is sub 0, that's saying my initial x value. It doesn't say that x is 0. It's saying it's your initial x value. So in this case, if I knew the function, I would plug in 1/4 as my x, and that would give me the height. And so I would be able to multiply whatever I get from my f of 1/4 times my width of 1/4, and I would be able to get that rectangle. Okay, so what if I didn't want to have all my rectangles in equal width? Or what if I wanted to have as many as I could squish in? And so if I were going to draw rectangles and find the height of my rectangle using my function, and I make them really, really tiny, I don't even have to make them the same size. And I can put as many in as I want. What's happening to my area as I do this? Is it the same as it was before, or am I actually getting a better estimate? And here where it curves a little sharper, I can make them even more tiny. And so I can get a more accurate value of what my area is. And so that's the basic idea of a limit. Let's push these rectangles to the limit. Let's get as many in there as we can. And then our area will actually approach the actual area under the curve. For our next exploration, we're going to be looking at a very blown up version of the function x squared. So our boundaries that we have are from 0 to 1. And in our first area under our curve, we're going to be using our left boundaries. So we have 0 as a value of x. We have 1/4 as a value of x. We have 1/2 as a value of x. And we have 3/4 as a value of x, because we're going to divide this into 4 rectangles. So using my left boundary, I'll just get you started. We have our function f of 0 determining the height of our rectangle, which we know 0 squared is 0. So this first rectangle, although it is 1/4 of a unit wide, it has 0 height. So 0 times 1/4, your first rectangle is a value of 0. So then your second rectangle, it has a height of 1/4. So you have f of 1/4 to determine the height. All of the rectangles are the same width, so you have a 1/4 width, and the rectangle comes across and then down. Your next rectangle is using f of 1/2, again with the consistent width of 1/4. Your next rectangle, f of 3/4, and then done. Now your second graph also goes from 0 to 1, but this time we're going to be using the right-hand boundaries to determine the height of our rectangles. So again, we're making our units at 1/4, 1/2, 3/4. And so our first rectangle has a height of 1/4, comes over a width of 1/4 as well. So f of 1/4, whatever you get for that, times 1/4. Your second rectangle has a height of 1/2 and comes over. And you can tell by either using the left or right side, I'll either get an underestimation for my area or I'll get an overestimation for my area. And just because it's so difficult for me to write, you can tell that mine aren't exactly perfect. You can do yours better. And then my final one has an f of 1. Estimate your areas for these, and we'll discuss this concept tomorrow in class. Okay, so the Google homework is very simple. It's just that one little graph where I asked you to estimate where is the sickness increasing, how many people are getting infected. And so where is that happening the fastest, between 1 and 3 and between 4 and 6. Other than that, everything else is just on paper and brought into class. These homework problems 1 through 8, 10 and 11, these will be assigned tomorrow night. So have a good night, and I will see you tomorrow.